Earth has been spinning through space for 4.5 billion years. Homo sapiens have been here for roughly 300,000. Our entire industrial era, every factory, steam engine, and power plant, has existed for about 300 years. This staggering gap is what prompted astrophysicist Adam Frank and NASA climate scientist Gavin Schmidt to propose the Silurian Hypothesis. They asked whether an advanced industrial civilization could have existed on this planet 50 or 100 million years ago without us ever realizing it. We operate on the default assumption that humans are the first of our kind, but stretching our timeline back by tens of millions of years forces us to treat the planet like a cold case. The immediate objection to this is obvious. If a sprawling ancient civilization existed, we would have found their cities, their bridges, or at least a fossilized smartphone. But that assumes human artifacts are durable.
If our species vanished tomorrow, it would only take a few thousand years for forests and jungles to completely overgrow our abandoned cities. Expand that timeline into millions of years, and you enter the realm of deep time. Tectonic plates shift, massive earthquakes ruptured the ground, and ice ages come and go. These geological forces act like planetary sandpaper, grinding every ounce of concrete, glass, and metal into dust. The Earth's surface is a highly efficient recycling engine. Given 50 million years, any physical structure placed on the crust is eventually destroyed. The absence of ruins is a natural consequence of geology. To find evidence of a precursor, we have to look past physical objects toward the specific chemical markers embedded in the rock itself. Since architecture is guaranteed to disappear, Frank and Schmidt shifted their investigation from traditional archaeology to microscopic chemical forensics. They suggest looking for techno-signatures, specific chemical markers permanently trapped in geological layers of rock, like the sedimentary bands seen here. Burning fossil fuels on a massive scale alters the atmospheric carbon-12 to carbon-13 ratio, leaving a permanent anomalous dark band in the rock. There are other artificial markers to hunt for. Synthetic chemicals like compressed microplastics or Teflon do not occur in nature. Neither do long-lasting radioactive isotopes like plutonium-244, which could linger in the soil for millions of years. Combine those synthetic chemicals with geological evidence of a sudden, severe spike in global temperatures and a massive die-off of animal species, and a distinct pattern emerges. The legacy of an industrial species is a permanent chemical scar, burned into the geological record for millions of years. This brings us to the crucial question: is there any moment in Earth's history that matches this specific profile? There is a candidate, the Paleocene-Eocene thermal maximum, or PETM. It occurred 56 million years ago. Look at this historical temperature chart. For millions of years, the climate was stable. Then, at the 56 million year mark, global temperatures violently spiked by 5 to 8 degrees Celsius, accompanied by a massive, sudden atmospheric carbon injection. The environmental consequences were devastating. Ocean ecosystems crashed, leading to widespread species extinction across the globe. The ancient geological data from 56 million years ago looks nearly identical to the chemical footprint humanity is aggressively creating right now through fossil fuels. Evaluating the PETM acts as a mirror. It shows us exactly what our own civilization's eventual destruction will look like when reduced to raw geological data. To be clear, Frank and Schmidt do not believe that ancient sci-fi beings built factories on Earth. Most scientists agree the PETM has natural explanations, likely triggered by massive volcanic eruptions or the catastrophic thawing of permafrost. The Silurian hypothesis was intended to be a thought experiment rather than a factual historical claim. The hypothesis functions as a framework for identifying industrial signatures, providing the specific data points needed to scan the rest of the galaxy for signs of life. By determining what traces humanity will inevitably leave behind on Earth, we learn how to scan for life elsewhere in the universe. Defining these earthly techno-signatures give astronomers the chemical blueprints they need when scanning distant exoplanets. If an industrial society collapsed on a world 1,000 light-years away, we now know what atmospheric anomalies to search for. Everything we have built over 300 years of industry, every machine, every city, every piece of technology, will eventually be compressed into a single microscopic layer of rock. Humanity builds monuments to be remembered, but our ultimate mark on this planet will be a subtle, anomalous shift in chemistry, waiting in the dark for whoever follows us.